It's coming.
Okay. Hi everyone. To begin the next presentation from Simone Deponti about Aside the Server Story. Please turn off your cell phones and enjoy.
So, welcome to Server-Side Story. It's, okay. First thing is, who am I? I'm a Python web developer since 2006. I mainly work as web developer, so I do web development. I contribute, I'm a Plone contributor. Plone is actually a content management system written in Python. And lately I've been doing far more JavaScript than I'm willing to admit here. But, okay. Next thing, am I in the wrong room? So, quick slide on what this talk is about. I'm going to do a little bit of history of the web, actually, very quick, to see how we evolved from certain models to other models and basically start adding use cases to a technology. And what are today's challenges to the web development model? Specifically, it's the challenge of real-time applications. I've seen already 3 talks which were about real-time applications this year, and I'll be presenting patterns and tools to deal with these challenges. It's almost code sample free because code sample tend to be very long and might be very hard to follow, so I'm not going to be showing a lot of Python code, but instead focus on patterns actually. So a little bit of history. In the very beginning, the web was about documents. So when HTTP and HTML were invented, the use case they were trying to solve was basically, I want to retrieve a document and give me that document. It's a very simple use case. So you ask the server that precise document, the servers give it back to you. The other thing was that you could link documents together, which back then was like something incredibly new, but nowadays isn't anymore. And so the technologies we are using every day were initially conceived, and their design was to solve this use case, which is fairly limited. Then what came next? Basically, okay, so you have documents, you tend to have a lot of documents, and then you start saying, okay, maybe I want to search them, or have any way to actually index them, or whatever. So the next thing they tried to solve was, for example, to add provisions to, for example, do some queries like, I don't know, can I have all the documents about this certain topic, or something like that. So they started adding query parameters, and then we started having post requests and then forms. And then we said, well, okay, why just have documents? We can just present programs as they are pages, and then we started having CZI programming. And we started going away from the concept of document, which was the origin. Then there was a problem because since it's a document retrieval system, state is not needed, so HTTP is absolutely stateless. But the thing is, an application, which is fairly complex, can't actually deal without some kind of state. So that was sort of added on top of it by using cookies, which is actually still the way in normal web applications that we deal with state. If you need to maintain some sort of state between 2 requests, you have to use cookies in some way or another. Sessions are, well, actually, they still use cookies. Then came JavaScript. Actually, in the very origin, HTML was, they added the script tag saying, well, okay, maybe in the future we might want to have some interactive documents or stuff like that. So they added this script tag and said, okay, well, we'll think later about what to put inside it. And which means that there was basically no standard language to deal with that. And then actually, yes, it was Netscape, invented JavaScript, or basically hashed it into production very hurriedly. And so we started to have a way to, for example, modify a document on the fly. But that's still limited. I mean, if you think of it, most you can do is add effects like, I don't know, transitions or hiding and showing elements. That's the most you can do about it. Then in about, I think it was in 99, Microsoft invented Ajax, which is a way to actually make a side request to the server, and started developing what today we call the one-page applications. Basically, we don't have documents anymore, but they are actually real applications. Once we have that, one of the strange things that happened is that since then, basically, all the programming was done server-side. The server had the data, the server had the state, and everything was controlled there. Once you start, I don't know, think about Gmail, for example, then you have even some sort of state on the client. And we'll get back to that later. And this is the first huge step in a way, because it's more complex to deal with that in certain cases. So what's the current situation? We are used to, these are fairly standard web applications where we have a server, which is basically we can call it the master. All the data is stored on there, and the client, basically what it does is to ask for stuff and get back a reply. In this model, the problem is, so what happens actually on the server side each time a request comes in? Since HTTP is mostly stateless and cookies or session are basically just a hack on top of it, every web framework nowadays does these steps. Basically pulls up the state, assembling it from the parameters it has, processes the request, assembles a response, and then gives it back to the client. And this happens on every request. It's and a lot of things actually were born on top of this model. If you think, for example, of, well, it's more of a Java thing, but they talk about inversion of control and this kind of stuff. It works only in this model because you have a very rigid set of steps. The problem with this model, where basically we have a client that access stuff and the server that gets back a replay, it's the problem where the server itself can't speak, or rather can speak only when asked. And this works well if you have a system where basically all you're doing is asking for stuff to be done and getting back the result. But sometimes you actually want the server to be proactive and give you back some feedback even if you're not actively challenging it. So this kind of use cases are, for example, notifications like, I don't know, someone just logged in on the system, or real-time data, or a chat system. For example, in the previous talk, one use case was, for example, to send real-time data to a dashboard, or, for example, gaming. And all this stuff falls into the real-time applications domain. And it's been only recently that we are starting to have more and more real-time applications, where actually the server is proactive and pushes data to the client. So what are the solutions up until now to this problem? In the very region, we started doing, because it's not the first time that this problem has been there for a lot of years. So the first solution that has been used, I don't know, how many of you has used polling in an application when they needed to, okay. Now, what's the big problem with polling, and you're probably very familiar with it, is that polling, keeping with the metaphor, is a bit like that. The client goes and says to the server, have you got something to say? Have you got something to say? Have you got something to say? And the server's like, oh, please shut up. I'll phone you back. So basically, what you're doing is you're wasting CPU, bandwidth, memory, just to annoy the server. And, well, that's not a good use of your resources. There are certain hacks like logarithm polling, like, for example, well, I can poll you very frequently, and then if you've really got nothing, I can poll you later and later, but this time it's not a solution because, for example, you start losing events. So a new mechanism needed to be developed, and a guy came up with this pattern. I don't know how many of you are familiar with the comet pattern. Okay. It's still based on the request and reply pattern, but it adds a bit of a hack where basically the server doesn't respond immediately, or rather does respond immediately with a very vague response, which basically is headers usually, and then basically loses time waiting for something real to happen, and then deliver the real response. So basically you do the request, the server sends back the header and says, yeah, I've got something to say, and then doesn't say nothing for a very long time. If something happens, the server then sends back, oh, look, something happened. Or if not, it lets the request die, basically, in timeout. And the client has to restart it. There's actually a fairly good protocolization of this, which is called Bosch. I don't know if any of you is familiar with that. Okay. It's basically using XMPP. XMPP as a way to basically tunnel connections over HTTP. And what it does is Comet, basically. What it does is that the client starts a long polling connection, so a connection to which doesn't expect a reply soon. If something happens on the client side, so while this request is open, the client opens a second request, and the server replies on the first connection and closes it, and then we still have another connection open. And then there is basically a ping-pong mechanism to keep connection opens and allow for timeout to be dealt with. But both these solutions actually are, well, most of hacks on top of the existing stack. Still, even if they're hacks, they present on the server side quite of a challenge, because if you have, I mean, the usual execution model of a web application calls for one thread or process to serve one single request. That's a problem, because if you have many clients that are basically connecting and just waiting for events, you have a stuck thread or a stuck process, which is even worse. And this doesn't scale, absolutely. So, I mean, it might scale for, I don't know, for threads probably you can go up to 100 or whatever, but still, your resources go down very quickly. If you think, for example, that you're Facebook and you want to implement your chat, you can do it with this model. You would need to buy more servers than probably there is space on Earth for. So, what you actually need on the server side to deal with it is an asynchronous execution model. Then actually, on the client side, we've resolved this problem with WebSockets. WebSockets were invented to basically have a way to channel an HTTP connection. Basically what is sort of a raw TCP connection through an HTTP connection. There was a talk by Roberto De Ioris today which explained the very boring detail about how the handshake and how the bits are transmitting and so on. It actually uses a provision that was made in the HTTP 1.1 protocol, which sadly, since it was sort of reserved for future uses, there were no use cases when the protocol came out. It's where certain proxy vendors or like hardware proxies said, well, okay, this part we can skip of the protocol. It's not important. Nobody uses it, right? Right now, people use it, and there is this problem with WebSockets where some people might not be able to use them because there is in the whole network stack and maybe out of the control of the developer, there is maybe a proxy that can handle the connection upgrade. So how do you do WebSockets in Python? This is the quickest example I could find. It uses gevent. Actually, there are other ways in Python to do WebSockets. You can use either Twisted, Tornado, or other asynchronous frameworks. But actually, I'm just using gevent basically because the example is very, very quick. Now, basically, it's very simple. What we have here is that we call a certain page, we get a WebSocket, and then the WebSocket more or less behaves like a standard TCP socket. That wait is actually like a receive for a socket, and send is actually send. But you can see in that I've highlighted a line, there's a while true, which means that that's a continuous loop. That's because since you're opening a persistent connection, you must leave it open. You can close and reopen it when it needs. So the question is that, okay, right here, if we weren't using gevent, we would have a problem because one process can handle only one request. Thanks to gevent, actually, I think this is a greenlet, and so multiple of these multiple instances of this code, if we can call it like that, can run together in the same process and not using threads. Now, asynchronous I/O, or actually any asynchronous framework, tends to be really hard because you're switching from a model which is very sequential to a model where basically you just have a component that needs to be able to get stuff, put it there for a moment up until an event occurs, and then accept immediately other stuff, and then call back if something happens. So if you think of it, the flow of your application becomes very complex. Okay, I've already said that processes and threads don't scale. But there are then two kind of systems. One is the callback-based systems. I don't know how many of you use JavaScript. Okay. So you're probably very familiar with callbacks. Callbacks are, for example, when you make an AJAX request, you have to provide a function to be called when the request happens. And that's a callback. But the problem is that developing an entire application on callback-based system can be quite hard for the programmer, not for the system. The system is very fast, but the problem you have is that it's quite hard to follow for the programmer. The other solution, which are green threads or coroutines, or some other calls them fibers. There are actually very small difference between all these denominations, but basically the idea is to have something that are like threads, but that don't use the operating system facilities provided for threads. So basically, it's like if the virtual machine provides its own little scheduler that's able to run code concurrently. And right now in Python, there is no clean and easy solution. What I mean by easy, callback systems are not easy. If you Google for Twisted or Tornado, you'll probably end up on countless blog posts saying how much they suck because you write stuff, you have a bug, you can track it down, it's so complicated. It's because, well, it's the design system. Callbacks are complicated. And the thing with green threads is that they must be supported at the very low level in the virtual machine. So we have a library that is gevent, but as far as I know, it does a little bit of shady things in the background. So of course, the problem with doing shady things is that while they work and it's well tested, and you can use it in your production code, it won't break. Still, it's not something very clean, and nobody feels very, very good about it. So actually, that's why PEP was made by Guido, the benevolent dictator for life, which basically tries to provide a common ground for all the asynchronous framework directly in Python. This is going to be Python 3 only because it's actually uses certain facilities that are not available on Python 2.x. So what it does, before we said that we had this thing, this while true. The while true is actually the most basic form of what is called an event loop. An event loop is basically just an infinite loop that's able to dispatch events to various pieces of code that then have to act upon what's happened. What it does, since event loops can be very customized, for example, you could have one event loop, or two or three or more event loops that are actually intertwined. It tries to provide a pluggable event loop interface, so basically it provides some basic event loops, but you can write your own. It then uses the concept of futures to abstract callbacks. Futures are, for example, also being used now. Most advanced JavaScript code is trying to switch to futures. The basic idea of a future is that when you call an asynchronous function, you immediately get a result, and that result is a promise. It's an object that's not really a result, because maybe the code was not even executed, the request hasn't returned, or whatever else. But you can use this object, you can pass it around, and you can add callbacks to this future object instead of providing a static chain of callbacks. It also, in this PEP, since Git itself is not very keen on using callbacks because he finds them difficult to write, and I totally agree, he added support for coroutines using the yield from keyword. I don't know how many of you knew about yield from. Okay. So basically, with yield from, he's able to basically have a cleaner implementation of green threads. Well, coroutines are not exactly green threads, but let's not go there. And it then splits the concept of transport versus protocols to deal with all the different input-output needs, because right now I'm concentrating on networks, but this could be extended, for example, to files. Reading a file could be asynchronous too. Okay, so considerations about this PEP actually has pros and cons. The thing is, if you go to the PEP and you read it, I, for example, had a lot of problems initially to actually understand it, because it's very long, it's almost complex, so it's not really straightforward where you read it and say, oh, genius. But what is these problems? Because we have, in Python, we have a lot of constraints. I don't know how many of you has actually tried to use Node.js. Okay. So if you ever try to use Node.js, you see that each API basically is asynchronous. They provide sometimes the synchronous version, but by default, every API is asynchronous. You want to read from a file, you don't get the result back immediately, but rather you have to say, okay, read from this file, and once you have the data, call this function. The problem is, in Python, it would be great if we could do this in Python, but we can't, because Python already has a standard library. JavaScript never had a standard library, so when Node.js came, they could say, okay, let's invent our own, and let's make it asynchronous, because it's better, actually. Also, the JavaScript developers are already used to using callbacks, so it's not a big of a deal. While on Python, we can't completely rewrite the standard library, because there are a lot of libraries, an entire ecosystem that builds on top of this, and if we reinvent the very base, then we have to restart from scratch and rebuild everything. And if you think how many times it took for libraries to pass from Python 2 to Python 3, you can just imagine how this is completely out of question. But the very interesting thing is that Tulip is actually, Tulip, sorry, is the provisional name for the implementation of this PEP. Tulip is actually a library designed so that frameworks can build on top of it and actually abstract it in a more, how can I say, developer-friendly interface. I don't know how many of you has actually used the thread standard lib library. Wow, way too many. Because, sorry, thread, not threading. Because you have a low-level API to deal with threads, and then you have a higher-level one. Generally, if you're going to use threads, you're going to use the higher-level one, so that abstracts all the boring details. It reduces the amount of errors you can make. And the idea of Tulip is to be a little bit like a thread library, upon which one or more different and more developer-friendly libraries can be built upon. It's actually planned to land in Python 3.4. And another thing that it does is that it provides wrappers, asynchronous wrappers, for parts of the standard library. So for example, each time you have to, I don't know, resolve a host name, that's present in the standard library, a call to do that, but sadly it's synchronous. If your application suddenly, and maybe even without not knowing, you trigger a name resolution, then you have a blocking call, which means that basically your entire application will stop up until that resolution is done. Because when you're developing an asynchronous, or on top of an asynchronous framework, every time you let the code block, your entire application blocks. No connections are served, no connections are accepted, everything stops. So Tulip actually has a fairly complex example that I've linked at the bottom for solving the WebSockets problem. Which is actually quite complete, so it's not a very easy example. And it's made to actually solve the so-called broadcaster use case. So basically, you receive a message from a client, and you want to send it back to all the other clients that are connected. Think of a chat system uses this paradigm. Someone sends a message, and to each one that's in the room, in the chat room, I have to send back that message. Sadly, the example, I was hoping to actually took bits of it, but it's very complex because it deals with different workers, and it has scalability provisions inside, and it's a little bit outside the topic of this. So let's now make a couple of architectural considerations about what having in your stack an asynchronous application means. It means that most of the stuff that you were used with normal web development, or tricks or gotchas, can't be used anymore. For example, one idiotic thing is that caching can be layered on top of the application. It's very common for web applications to say, okay, I'll put a reverse proxy in front, so I can actually lift some of the workload from the backends, and that's actually a very quick and simple way to scale. You just put a lot of caching in front, and suddenly your application scales immediately. Sadly, you can do this, and which means you can't even mask problems. Caching is very useful, even if some parts of your application aren't that fast because, well, they aren't very well programmed. We hadn't time to find better algorithms or faster stuff. You just put a cache on top of it, and you're done. The application scales, and everybody's happy. In the asynchronous land, you can do that. Also, you must be very careful about how your code flows, because if there is, as I said before, if there is any moment where basically you make a blocking call or something goes wrong, then your entire application, since it runs in a single process, actually, or a single thread, your entire application will go down or block, which is even worse. And the other problem is that still, in an asynchronous application, you probably still need to, for example, read data somewhere, like connect to a database. Sadly, if in basically every driver for a database system is synchronous, which means that if you have to fetch data from a database, you have to resort to tricks like, for example, okay, I create a thread just for that, connect to the database, execute the query, retrieve the data, and send it back, and then have this separate thread that's being created go back into the whole asynchronous event stuff, and you have to orchestrate them because so you basically have to spawn threads that once they are done, they send back an event so that the asynchronous framework can deal with the response. That's, for example, what Twisted does when it has to deal with database connections. And of course, this means that if you have too many connections, if like for every query you just spawn a thread and let it die, your application might not scale very well because then you don't know how many threads the application is spawning under load. So you have to start with thread pools and fine-tune them. It's actually quite complicated. And the other thing is that basically, as I said before, once you start dealing with real-time applications that are more complex than just sending back some data to be displayed on a graph, you start having the state both on the client and on the server. Because since the client in itself is its own application and the server it's another one, then basically each part has its own state and you have to orchestrate it. Think of, for example, one application that needs to solve this problem is Google Docs or Google Drive. I don't know if any of you has ever tried to actually, two people can connect there and try to edit the same line. If you play a bit with it, at some point the Google Drive will break and tell you to reload the page because it's very complex for it to deal. You have basically you have two clients. Each of the clients has its own idea of how the page looks, what characters are in the document, and the server inside has its own representation of the page, and it has to try to coordinate these three representations. Luckily, this is a problem that this kind of architecture has in common with basically clusters. I don't know how many of you are familiar with vector clocks? Okay, one. Yay! Actually, the idea is that there are cluster systems have the same problems where basically you have multiple nodes and each node has its own state because most clusters are designed to work even if they get partitioned, so all nodes are not connected. So the state is actually spread out onto multiple nodes, and you need to reconcile the information between the different nodes. And so, for example, vector clocks are one method to deal with these problems. And the people that are doing large clusters are actually inventing more and more techniques. So there is a lot of theoretical work that can be reused to solve the same problem with a client and a server. As far as I know, Google Docs uses some of these techniques, for example, if two people are editing the same page to reconcile the changes made by the two people and come up with a representation that's correct for a certain value of correct. Actually, once you have solved this problem of the shared state, scaling it's not that hard because actually a single process with an asynchronous, basically an asynchronous framework, is able to handle thousands of connections by itself. Then, of course, you can put multiple processes on the same machine, and then if you still need more, you can scale multiple machines. And since you already solved probably the problem of the state being shared, actually having all these multiple processes reconcile with themselves, it's exactly the same thing that you did with a single client and a server. You can just replicate the model. So basically, we go from a client-server architecture to more of a peer-to-peer architecture. Of course, it's not all flowers, because since the control flow now is bidirectional, you can have the same amount of scaling that you had with normal web applications, where you could have caching that basically keeps a static copy of whatever processing request and just serves it back stupidly to everyone that asks it. So of course the scaling can be, you can't scale that big how we are used to with normal web applications, but still you can be able to scale very well. And okay, a little bit of security considerations. WebSockets actually were designed with a fair amount of security provisions. But most of the security provisions of WebSockets are actually against blatant abuses or man-in-the-middle attacks. Which means that basically it's clearly stated in the RFC, WebSockets do not handle any kind of authentication or authorization. Basically the only thing they do is to ensure you that the client connected to a certain connection is still the same guy and hasn't changed it in the meantime. The other problem is that the protocol, it's actually, well, fairly new, and because before it became final in the RFC, in the security part of it, appeared actually that they made a test and found that, for example, many proxies could be completely poisoned by doing a certain type of attacks. And so I think it's WebSockets are not enough mature to say, oh, okay, everything, all the security provisions that are in the RFC are fine. So if you're doing something that needs high security, don't use WebSockets, and actually probably don't use asynchronous stuff at all. WebSockets actually are very concerned with a browser web server interaction. The RFC states that basically you can use it even if you don't have a browser but some kind of other client. My idea is that you shouldn't, basically, because it's not a very well thought out use case. It's basically they said, well, yeah, technically you could have a client that's not a browser, but how can I say? No more work seems to have been done on that use case, so that there's probably some hidden stuff. And the RFC actually states, quite in big bold letters, that you must absolutely validate the data on both sides, from the client and from the server. This is normal, but usually people don't do it a lot on the client side, for example. Most of the times they don't. And the other thing that you absolutely need to do is to resist the urge to invent a sort of a protocol where you can basically send complex objects or even classes back and forth between client and server. I don't know how many of you knew about the Ruby security problem that there was. Well, okay. Basically, this problem was that they've been able to exploit the fact that most Ruby on Rails servers accept any kind of JSON object. And they've used that to actually execute random code on the server without any kind of authentication or whatever. It was a really, really nasty bug. And okay, 6 minutes. Recapping a bit, real-time applications are actually, I say, a big step for how we used to deal with the web. It's the paradigm, I think, has changed a lot, and that needs to be addressed. You can think of doing real-time web applications using the same techniques or the same tricks that you used before. It's like very, very, very different. Which means that everything that's server-side should actually, well, at least for the asynchronous part of the application, should totally abandon the standard model and instead go through asynchronous systems. Sadly, this is, well, actually, since most applications are probably a mix between a standard web application where the request and replay pattern is more than enough, and doing the normal kind of applications with an asynchronous system is just an unnecessary pain in the ass, actually. It's probably better for now to use hybrid systems where basically instead of one single front end, you have two front ends, one serving asynchronous request or like WebSockets or Comet or whatever else, and the other one serving the normal requests. This is a very common pattern. And in Python, we have actually right now production-ready tools to deal with asynchronous stuff, but right now they're very fragmented because we have at least 3 major systems, which are Twisted, Tornado, and gEvent, to deal with the same problem, and each is different from the other in its own way. And so it's not easy to choose a way to do it. But in Python 3.4 probably hopefully, we will have a common layer to address this problem, and basically we might have a standard way of doing asynchronous in Python. And well, of course, this area, as far as I can tell, it's still quite young. It's probably just a couple of years that we start having really big deploys of these kind of applications. And so, for example, the area of security, I think it's not very well developed, and will need some more time to actually be completely my English to be completely deployed. Okay, questions?
Hi there. I just had one comment on sort of the asynchronous thing and dealing with the databases. I found
Yes.
you mentioned then you have 2 things for asynchronous and 1 for synchronous calls. Well, actually, there's another way of doing it. You separate your application out into the bits that are the business logic and the bits that block that talk to the database. You have the Tornado at the front, and it's solely about getting the millions of people in, and they just wait, but you keep answering questions while you talk to your services in the background. I mean, that's another way of doing that.
Yes, it's okay. Did everyone hear the? Okay, so yes, but on the other hand, because I've actually tried to do that, and the problem is that you end up having an architecture that's much more complex. You start having a lot of moving parts. So if you have to build the next giant system that's already have to go on the cluster, then it makes a lot of sense. If it's a smaller system, I don't know. It's a lot of moving parts, and moving parts can create problems. So as a design choice, I tend to have fewer moving parts as possible, so not to have problems.
Hi, on the security point of view, is there such a thing as WebSockets over SSL? Or?
WebSockets have basically SSL the same as HTTP requests, so you can tunnel them through SSL. Okay. But the problem is that still you could, well, actually there is, if there weren't the security provisions that are in the protocol, there is, for example, a very complex handshake key, and the ping-pong mechanism is slightly more complex than one would imagine. That's because even if the connection is SSL, it's probably still possible to do a man-in-the-middle attack and just impersonate someone else after the connection has been opened. Okay, no more questions?